Alright, so we're going to do three methods for reducible second order differential equations. So our first one will be where we have a linear x term. So we say x, y, double prime, so that's the second derivative, plus y prime, so equal to 4x. So actually what we will have to do here is we're going to do some more substitution. So we're going to set dy over dx, derivative of this equal to p, and then we're going to say that the second derivative of x is equal to, the second derivative is equal to the first derivative is equal to the derivative of the first derivative of y. So that's going to just be equal to dp over dx. It's going to be respect to x, of course. So we're going to be using this to plug it in. So we're going to use this. We're going to say x times dp over dx plus p, because y prime is dy over dx, equals 4x. Alright? So actually, from this is actually going to just become something where we can use the integrating factor. So divide x on both sides. We're going to get dp over dx plus 1 over x times p is equal to 4. Alright, so now our integrating factor is going to be x is going to be equal to e to the integral of 1 over x dx, and that's just going to give you x. Alright, so once again we're going to multiply everything here, so x dp over dx plus p is equal to 4x. So now we know the derivative of x, our integrating factor, times p is equal to 4x. I'm going to integrate both sides with respect to dx, and then these just cancel out, so it just becomes x times p, and then the integral of this is 2x squared plus c, but we're going to have to call this c1. The reason is we know p is also dy over dx, so we're going to have to do a second differential equation. So we're going to call this c1 because we're going to get multiple different c's, which are not going to be equal to each other. Divide x on both sides, so you're going to get p is equal to 2x plus 1 over x times c1. Now we can finally do our substitution. Dy over dx, which we set to p earlier, is equal to 2x plus 1 over x c1. We can times dx on both sides, so this just cancels out here. We can find the integral with respect to both sides, so the right side will just become y. This side, well, the integral of 2x is x squared. Integral of this is c1 times ln of x, and you have to add another c, and that's c2. So yeah, so this is what it's equal to, but we like putting it in a general form where like it looks like more like visualization when you graph it. So you're just going to say y is equal to x squared plus a ln to the x plus b. This can also be ln to the x to the a, but it seems more simpler this way. So we quickly, so yeah, actually never mind. Yeah, so it becomes more of like a general form. And how to solve for this a and b, you're gonna have like you're gonna need specific values of, so like usually like y of some point. Usually I think you need y of 0 and y prime of 0. So yeah, you don't have that in this case. The next one is pretend you didn't have an x term there. Now, of course, because we set it over to dp over dx, we were able to have an x term to use properly. But if we didn't have that, pretend it was like all y's. Y times y double prime plus y prime squared is equal to 0. We're going to set dy over dx to p again. However, we're going to set d squared y over dx squared. We're going to set it to something that's equivalent to it. So this is just going to be p times, just going to be, well, I mean, I guess what it is basically, if you simplify it, you do some like manipulation, you'll just get to this. I'm not going to explain it, but good to just remember this, that these two, that this is just equal to the second derivative with respect to y. Oh, yeah, so like, because if p was dy over dx, it's dy over dx times dp over dy. These cancel out, so it just comes dp over dx, which is what we set to it last time. But because we can't use an x term here in any case, so those x terms cancel out here. So right, so that's equal to that. So now we're gonna plug that in. So we're gonna say that y times p times dp over dy plus p squared is equal to 0. You're going to say y times p times dp over dy is equal to negative p squared. Now we're going to try to get everything on one side. So because the dp is over here, you're going to get 1. Well, we're going to keep the negative there. So we're going to say 1, negative 1 over y dy is equal to p over, so that's going to be 1 over p dp on this side. Integrate with respect to each other, and you're going to get here negative ln y plus c1, remember, is equal to ln of p. I'm going to have to find out what this is equal to, what p is equal to. So we're going to do e on both sides. So you're going to say that the absolute value of p is equal to, well, I guess, well, I mean, let's first make this, to make this easier, we're going to make this 1 over y. And this is equal to 1 over y times e to the c1. So 1 over y times e to the c1, which we know is just equal to, this is just another c value, but we have to make the c2, because we can't consider them the same constants. So we're going to say it's equals c2 over y, and this absolute value will just make it plus or minus, but because both of them are related to the constant, we could just keep it in this form. So now we know that dy over dx is equal to c2 over y. Say c2 dx is equal to y dy. Integrate on both sides. This side's going to be y squared over 2 is going to be equal to c2x plus c3, and times 2 on both sides, so it becomes 2c2x plus 2c3 is equal to y squared. So yeah, I guess we only really, do we really only need the, I mean, do we only need the, I guess you should keep in the form of y is equal to ax plus b. I don't think you should take the square root here because of the positive, so I think this is how you leave it. So yeah, so that's the second method. And now it becomes easier to visualize using these constants, because it's like, if you know like the quadratic standard form, you would say like ax squared plus bx plus c, so using the variables a and b just makes it easier. Now the last method, so pretend you didn't have a linear term of x or y, you're just going to use this first method just because it'll be much easier, where you just said p equals dy over dx and then dp over dx, the second derivative. But now the third one is actually pretty neat. So I'll show you like this. So pretend you had y prime double prime minus 9 y prime plus 21 is equal to 0. Alright, so if you think about this, this kind of looks like a quadratic. I mean, if the double prime was a square and y, if this first derivative it was a linear term of y, it would just been y minus 4 times y minus 5, that's equals 0, and you're going to get the roots y equals 4 and y equals minus 5. So what we want to do is we want to transform this differential equation into something quadratic. So what we do is we set y equal to r to the we set y to r e to the rx. The reason we do this is we know the derivative of e to the rx, because e to the x is just a chain rule, you're going to get r to e rx, and you get y prime is equal to r squared e to rx. Why is this cool? Because we can factor out the e to rx. So let's just first plug this in here. So because we know each term has something e to the rx, I'm just gonna factor it out real quickly, and then we're gonna say r squared minus 9 times r plus 20 is equal to 0. How neat is that? Well, so remember, e to the rx can actually never, I don't think, maybe complex numbers it can be 0, but if r squared minus 9, r is equal to 20, so this is going to equal to r minus 4 times r minus 5. To be set to 0, that means r is going to equal to 4, or r is going to be equal to 5. And because we set our solution here y to e to rx, that means our solutions is equal to y to the e to 4x, or y is equal to e to the 5x. But because it's not like two different solutions, it's more like a combination of the solutions. So instead, we actually say that y is equal to a to the e to the 4x plus b to the e to the 5x. And this will still satisfy that equation. So, and then the a and b values, you can only find that out if you have like what y over 0 is and what y prime over 0 is. And actually, I'll show that tomorrow with Laplace transforms, because it's another way for second order, and it's very similar to this method, especially if you have on the right side e to some power. So yeah, those are like the three main methods for starting off with reducing second order differential equations. Thank you.